Saxon Algebra 1. Welcome, greetings, students, to the last week of new lessons for the year. We're on 117 today. Yay. Remember that the other students who are not in this book are skipping around a little bit this week because they have more than 120 lessons, so I'm cherry picking the best ones. You guys have exactly 120, so you're just going straight through. Okay, back in lesson 113, we talked about direct and inverse variations. And I told you some stories about toddlers taking toys off shelves and dads eating a lot of pizza. And we had some formulas for that. For the direct one, it was A equals K times B, where A and B were the two elements and K was some constant. And remember, they were two-step problems where we would solve for K with one set of numbers, and then we'd be given a question about a different scenario, and we would have to use our we'd have to calculate K and then use K to solve for the second situation. Okay? And remember, the rule was don't overthink it. Just just get the formula out of the problem using the sentence as it flows. Like, don't worry about rearranging the different elements. Just use it as it's written. And then we had a different formula for the inverse relationship, which was A equals K over B. This is the one where for every toddler that walks in the room, they get out 45 toys. And this is the one that as more dads come into the room, the supply of pizza goes down. Or maybe I said teenage boys. Teenage boys it works really well for too. All right, so this is where things are moving in opposite directions. This is when they're moving in the same direction. Today, we're going to put just an ever so slight spin on this by saying that sometimes the problem will tell us that one of the items is squared. Again, we'll just go with the flow of the sentence. We won't overthink it. But sometimes we will have a squared element. So this was lesson 113. This is today's lesson. The problems work exactly the same. We're given information. We solve for K, then we use K for the mystery. We'll just use this set of formulas. We have 3 problems. I think we have 2 direct and 1 inverse. Let's see. There are 3 problems though. Let me just double check. Yes, I'd be so sad if I lied to you. I mean, it wouldn't be a lie, it would be I was wrong. The distance required for an automobile to stop is directly proportional to the square of its velocity. Uh-oh, that sounds like physics. That sounds like acceleration and deceleration problems. I don't care. I don't know a lot about that, but you know what? I can whip these numbers into shape, and that's all we have to worry about. All right, so what we're finding out is the distance required for an automobile to stop. So I'm just going to use D. Is directly proportional to, okay, so that tells me it's one of these two. It's directly proportional to the velocity, the square of its velocity. Okay, velocity squared. Distance, okay, I know what distance is. That's like how long. Velocity, I know, is a lot like speed, right? So it's more of like a rate. So that kind of makes sense to me. The faster you're going, the longer it's going to take you to stop. Okay. I was thinking about this today because there were some kids riding their bikes, like older kids, like your guys' age probably. And my neighborhood is on a big hill and I'm at the top of it. And they were riding their bikes down the street past my house and they were cooking. They were going really fast. And I mean like bicycle bikes. They were flying, and this is at the top of the hill. And at the bottom of the hill, the road, the street that goes through my neighborhood turns out onto a busier street that has an even bigger hill. And I'm thinking, crap, I hope their brakes are working really well because they're going to come flying down this hill and then have to come screeching to a stop so that they don't sweep out into that. I'm like, I hope that they know their stopping distance as well. Okay, that's enough though. 1. If a car can stop in 200 meters, okay, that's a distance, at 20 kilometers per hour, okay, the velocity is like a speed, so 20 kilometers per hour. We don't have to put down the units on these. What will be the required distance when the velocity is 28 kilometers per hour? Okay, so I got these two. I'll use these to solve for that, and then I'll use it to figure out this. Now, the only thing that we have to do is just remember to square, right? Because we're using this formula. There it is. So the distance, 200, equals k, mystery, times 20 squared. Okay. 20 squared would be 400, right? 2 squared is 4, and then the 0 gets doubled. So I'm just going to cross that out, and then I'm going to divide both sides by 400. K equals 1/2. Or you could write it as 0.5. Your choice. Would you rather work it with a fraction or a decimal? Normally, you know how I feel about fractions. Mathematicians prefer fractions, but scientists, which we're kind of in the science world right now, scientists are crazy about those decimals. So I leave it up to you. And you can work it however you want. And then if John provides his answer in the other form, whichever he chooses, it's easy enough to switch back. All right. So now we're ready to use our value for k over here. So the distance is what we don't know, but we know it's going to be equal to, there's our formula, our constant, I'm going to use 1/2, times the velocity squared. Okay, now we can't cancel here yet. We have to square this number before we can adjust it, right? So I'm going to multiply 28 times 28. I don't know that in my head. 8 times 8 is 64. 16 plus 6 is 224. Put down a 0. And I get 487 equals this, right? So then distance is equal to 784 divided by 2. That's another way to approach that, right? All right, and I can see, it's going to go in there because it's even. 2 into 7, 3 times. 6, 18, that would be 9, right? Bring down the 4. There. So the distance required is 392 feet. No, meters, because we're working in metrics in this one. And that's the right answer. Okay, so the only thing that made this problem different than the ones we were doing in 113 is we just have one more step in the simplification process of dealing with the square. So easy. It makes you feel smart, right? It should make you feel smart. 18.2. All right, I'll read you another story. The distance a body falls. Oh, I've got a story here. The distance a body falls varies directly as the square of the time it falls. The distance that a body falls varies directly with the square of the time it falls. Right? Varies directly means I write them together. If it said it varies inversely, I'd put that on the bottom. The distance of a body falls varies directly as the square of the time that it falls. Okay, I have to tell you a story. Time out. When I was in college, I studied accounting. When I graduated, I went to Michigan State University, and I grew up in Michigan. And after I was done, I got my dream job at a great big public accounting firm in Chicago. And I loved my job, and it was really fun. And I was like a corporate lady wearing my suits and my floppy bow ties and working in this really cool office. It was a really, really great fun job. And I worked right downtown in Chicago, and I loved every minute of it. We had like cubbies, you know, the partitioned little things where you work. And there was a big window. And in my little section, it was like this. There were 3 little desk units here. And then there were some in the middle. And then there was another set of 3 here. It was called a staff room. They were built in, actually, so they went the whole length, right? Like this. And this one was mine. Okay? And this window looked out onto one of the busy streets in downtown Chicago. It was called Monroe. And across the street was a big building. I don't know what it was exactly, but probably had offices. But it had, you know, a bunch of stories and a bunch of windows. We were on, I want to say the 14th floor. And so this building, you know, our building had, I don't know, 60 floors maybe, and the one across the street had similar, right? So they were big skyscrapery buildings. It was fun. And one morning, I had come in, and I was standing in my area, and I was standing up, leaning on with my elbows, you know, like propped up, talking to my friend Paula, who was here. This is Paula's. Okay, so I'm looking, you know, roughly at her like this. And all of a sudden, it was like 8:15 in the morning. All of a sudden, I saw a human being falling through the air past the window. Somebody had jumped out of this building and was falling to their death on the sidewalk below. It was absolutely bizarre to be standing there looking out your window and suddenly see a human being go by. It was a man. He was wearing like a dress shirt and a tie and pants. Like, he didn't have his jacket on, but he was obviously like dressed for work. And he fell. I can still see it. And it was like 1981. Paula, I was like, oh my gosh, did you see that? And some people sitting over here had seen it. Paula was like, no, what are you talking about? Because she had been looking at me, right? And the other people jumped up and ran down, and they were like, don't look, don't look, don't look, don't look. So Paula and I were like, okay, we won't. But that's my story, so that whenever I do this problem, the distance a body falls varies directly, I get a little bit triggered. It was a horrifying experience, but sort of fascinating just to see this body, like it was falling really fast, but I had a very clear visual snapshot of the motion. And I'm so glad that my coworkers told me don't look out the window, because that would have been bad. Okay, the distance a body falls. Ouch. Okay, if it falls 144 feet in 3 seconds, okay, so that would be the time. Sorry, I'm just like over my story now and moving on. It was really intense though. If it falls 144 feet in 3 seconds, how far will it fall in 10 seconds? Okay, so there's my first scenario. Second scenario, there's my formula. There's my old staff room at Arthur Anderson. And now we can set up our problem. Ready? First step is to use this information to solve for K. Distance, 144, equals K, we don't know what it is, times T squared. T is 3, so it's 3 squared. 3 squared is 9, so I'm going to write that there, and then we'll divide both sides by 9. Right? That'll cancel. And now I need to do 144 divided by 9. Goes in there once, that's 9, that's 54. Okay, 16, right? 9 times 16 is 144, so we get K equals 16. I'm good with it. Are you? All right. I know you're probably still disturbed by my jumper story. I never found any story. I never heard any like news of what happened or anything like that. I mean, I assume the guy jumped, but maybe somebody pushed him or threw him out the window. I don't know. It's too horrible. All right, now I'm upset all over again. All right, now we're ready to take this number into the second part of the problem and say the distance equals k times the time squared. Only the time gets squared, so make sure you write that carefully, right? I didn't need parentheses on this for sure, but you do need it here. Okay, that is 16, 10 squared is 100. So my final answer is that. It's a distance. So I look and see what kind of distances we're getting. It's feet. So there's our final answer, and that's correct. Many years after this story happened, my husband, who worked with me at Arthur Andersen, that's where we met. But many years later, he was working at his job. This was 2008 or 9, maybe. He worked at an office in Fremont. The company he works for is called Institute of Systems Biology. It's a medical research institute. They have scientists all over the world doing research, and they use data from Swedish hospitals, and they study all kinds of cool diseases, including COVID. They're doing a COVID study. The study they're doing, oh, now I'm getting stories on my stories, but I think it's interesting. Their COVID study, they're part of a study that is trying to figure out how come some people get COVID and are barely sick at all. Some people don't even know it. Some people just get a mild cold. Other people literally die an anguish death from it. How come it's so different for different people? That's what they're studying. Anyway, my husband had an office on, oh gosh, I forget the name of the street. I think it's Fremont Avenue, maybe. It's down, if you've ever been in Fremont, it's the one that runs right along the water. And then when you look up, this is his office here. Okay. And this is the street. I forget the name of it. But when you look up the hill, there's the troll up there. You know the Fremont troll that's holding the Volkswagen Bug? Right? He's got a car in his hand. I think it's this hand. And he's a big shaggy-haired troll, and he's underneath the bridge. It's really cool. If you don't know what I'm talking about, stop right now. Yes, I'm serious, right now, and Google Fremont troll. Anyway, the bridge goes over his office, and somebody jumped off the bridge, and he saw it. And it wasn't pretty. So there, 2 suicide stories for you. I'm very sorry. Okay, let's do one more problem. I need to move on from that page. But seriously, if you don't know the Fremont troll, you should Google it. It's a really cool Seattle landmark, and you need to go there someday soon. All right, the weight of a body on or above the surface of the earth varies inversely with the square of the distance from the body to the center of the earth. What? I don't even know what that was about, but I know it was something complicated. I'm going to go through and try to just ignore the words that are extra and just focus on what helps. The weight of a body on or above the surface of the earth varies inversely with the square of the distance of the body to the center of the earth. All right. Weight varies inversely with the square of the distance. I just fished through all the words and tried to find the simplest part of it, and that's what I came up with. All right, this is honestly the hardest part, is just picking through all the science words and finding what you need. All right, here come our 2 scenarios. If a body weighs, and honestly, if you're having a hard time, go ahead and look and see what information they give you. Because John tells me if a body weighs 10,000 pounds, when the distance is 5,000 miles, how much would it weigh when the distance is 50,000 miles? Okay? if I would have been super confused here, trying to figure out what letters to use, if I go into the numbers and see what the units are or the words are that John gives me, that can help me figure out this, right? I can see the W and D more clearly in this part. All right, I hope that made sense. I wish I could see your faces right now to see if you're giving me that. What are you talking about? All right, so we're going to use this to solve for K. 10,000 equals K over 5,000 squared. Oh, that's going to be kind of a big number. I mean, it's kind of simple, but it's a lot, right? This number is going to be 25, and then 1, 2, 3, 4, 5, 6 zeros. Am I right? 25 million? What the heck? That's a really big number. And then to solve it, we are going to cross multiply, right? We can think of it that way. K times 1 is just going to be K, but I'm going to multiply that times that to get my value for K. So K equals, whoops, I didn't need that there. 25, 6 zeros, 1, 2, 3, 4, 5, 6. Oh, I'm not gonna, my commas I'm gonna have to change. And then 4 more zeros, 1, 2, 3, 4. 2, 3. Okay, it's 250 billion, million, thousand, hundred. Okay, that's a really, really big number. So what we can do is write it in scientific notation. I mean, perfect, right? This is exactly what scientific notation is for. We want to move the decimal place there. It's currently here. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2.5 times 10 to the 11th power is our value for K. Wow. That's a lot, isn't it? It's correct, but that's a lot of zeros, which is exactly why we want scientific notation. I don't want to keep track of those. I get a headache just counting them all. All right, so now we're ready to do this one. What is the weight when the distance is that? Okay, so I'm going to write this 2.5 times 10 to the 11th over, now I have to square it, right? 50,000 squared. All right, this is going to be a big number too. Let's write this in scientific notation and see what we can get. The 5 times the 5 is going to be 25, and then we'll double the zeros. 1, 2, 3, 4, so we need 8. And that comma is going to be wrong. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's move it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2.5 times 10 to the 9th is this. Does that make sense? I hope so. Okay, so we can cross that out because we changed it to this. Now we can simplify this, right? I'll just write it again so we can see it. 2.5 times 10 to the 11th over 2.5 times 10 to the 9th. That cancels, because that's equal to 1, right? And we don't even need it anymore. I mean, I guess we can keep it, but that just simplifies to 1. And then remember, the rule here is we subtract. So this will be 10 to the 11 minus 9, which equals 10 to the 2. So our answer is 1 times 10 to the 2, which equals 1 times 100, which equals 100. And now we just need the weight. Pounds. That's how much the person will weigh when they're that far out. Weird, right? Is that the right answer? Yeah, that's the right answer. Okay, yay. And this is W. I stopped writing it way up there. All right, so I like this example because it shows how scientific notation can actually be helpful instead of just a pain in the neck all the time. All right, that is lesson 117. Never again will I send you a lesson on a Monday morning. Aw, I'm sad. Goodbye.